Okay, so let's take a look at this here. So we have a glass container that can hold an internal pressure of 195 kPa before breaking. The container is filled with a gas at 19.5 degrees Celsius and 96.7 kPa and is then heated. Predict the temperature at which the container will break. Okay, so we have this temperature and this pressure, right? So T1 is 19.5 degrees Celsius, right? So if we do 19.5 plus 273, we get 292.5 Kelvin. And P1 is 96.7 kPa. Okay, so T2 is what we're looking for. We want to know what temperature will it break at, and the pressure is 195 kPa. Now, I know we haven't done an example yet, but remember that if the pressures were not the same unit, you'd have to make sure that they were the same. So we have P1 over T1 is equal to P2 over T2. So we have 96.7 kPa over our T1, 292.5 Kelvin is equal to 195 kPa over T2. Okay, so cross multiplying this once again. So we end up getting T2 times 96.7 kPa is equal to 195 kPa times 292.5 Kelvin, right? So you divide by 96.7 on either side. Right, you don't have to show this step, but I'm just going through this in case anyone needs to see how we're getting these values. So this is going to be 195 times 292.5 divided by 96.7, which ends up being 589.84 Kelvin. Now, anytime you're asked to solve for temperature, the question does not say it, but it kind of is naturally, it's like a known thing that because you are given the original temperatures in degrees Celsius, you should be reporting this in degrees Celsius. So remember, to do that, you would just simply subtract 273. So if we do that minus 273, we get 316.84 degrees Celsius, and then our sig figs is 3. So this would be 317 degrees Celsius. Okay, so the last part of chapter 11 is actually something called a combined gas law. So it's really kind of nothing special. It's just literally a combination of all three of the gas laws that we've already learned. So we have P1 V1 over T1, P2 V2 over T2. Now, what happens with these changes is a little bit harder to predict here because you have three different variables changing at once, okay? So keep in mind, right, the same rules apply. The pressure has to stay the pressure is the same unit, volume has to be the same unit, and temperature is still in kelvins, right? Nothing there has really changed. So how you know you have to use this law compared to any of the other ones is you have to think about what is changing. So in this case, when you're dealing with the combined one, all three variables means that they are changing. Like there's a different pressure, a different volume, and a different temperature, right? If we go back to this one for a second, this was only dealing with pressure and temperature. There was no volume whatsoever discussion. So if you have only two things changing, you use the law that has to do with those two things. If you have all three things changing, you have to use the law that involves all three variables, right? So you have pressure, volume, and temperature changes, right? So this calculation is used when you notice that the question involves a change in all three variables. Temperature is always in Kelvin, so that is not changed, and I already mentioned that. Okay, so we'll do one example and I'll have you try one out on your own before we continue with the video. All right, so a balloon contains hydrogen gas at 20 degrees Celsius and a pressure of 100 kPa and has a volume of 7.5 liters. Okay, so we have a bunch of stuff here. So let's just write this all out. So we have 20 degrees Celsius in Kelvin. This is going to be, what, 293 Kelvin, right, plus 273. we have a pressure of 100 kPa and a volume of 7.50 liters. Okay, so calculate the volume of the balloon. So we know we're calculating for the volume. After it rises 10 kilometers into the upper atmosphere, where the temperature is now negative 36 degrees Celsius, right? So negative 36 plus 273, we get 237 Kelvin. And the outside air pressure, so P2, is 28 kPa. Assume no gas escapes and the balloon can expand to allow for the pressure to remain equal to the outside air pressure. Okay, so notice this 10 kilometers. For some reason, students think that if just because there's a number in the question means that we have to use it. Not necessarily. They're just literally just telling us where is this balloon flying to, okay? But notice there's a different temperature, there's a different pressure, and they're asking us to solve for the new volume. So all three things are changing. So we're going to use all three variables, P2, V2 over T2. Okay, so let's plug this in. So we have 100 kPa, and then we have 7.50 liters over 293 Kelvin is equal to, so P2 is 28 kPa. We're looking for V2 over T2, which is 237 Kelvin. I said it right, but then I didn't write it right. Okay, so we're going to do cross multiplication here again, right? So we're going to have 293 Kelvin times 28 kPa times V2 is equal to 100 kPa times 7.50 liters times 237 Kelvin, right? We want V2 to be by itself. So just like we always do, you have to divide by whatever it's with. So in this case, the only difference is there's two things that are there, but it's the same process. 293 Kelvin and then 28 kPa. Right, so these cancel. And then if you look at the units, right, kPa cancels and Kelvin cancels, you're left with units of liters, which is what we should have. Okay, so it ends up being 100 times 7.5 times 237 divided by 293 times 28, which ends up being 21.666 liters. And then for units of sig figs, remember we're not using this 10 kilometers, but 100 still has one significant digit. So actually this would round to 20 liters, right? Because it's closer to 20 than it is to 30. Okay, so you have all three variables changing. We have the combined gas law. Okay, so let's take a look at this one. So steam is used in a hydroelectric plant to drive the turbines that produce the electricity. Determine the final pressure of the steam that is converted from 10.0 kiloliters at 600 kPa and 120 degrees Celsius to 18.0 kiloliters at 110 degrees Celsius. Okay, so if you want to pause the video here, you can give this a try and then see how you did. Okay, so we have V1 of 10.0 kiloliters. Now, you don't have to convert this because we have both units of volume at the same. Like they're both kiloliters. So remember, it does not matter what the unit is as long as if you are being consistent. So temperature 1 is 150, which is going to be, so 273 plus 150, oops. Okay, so that's going to be 423 Kelvin. V2 is going to be 18.0 kiloliters. P2 is going to be 600, oops. No, P2 is what we're looking for in front of me. P2, we don't know. And then T2 is going to be 110, which is going to be 283 Kelvin. Okay, so we have P1, V1 over T1, P2, T2, pardon me, P2, V2 over T2. I'm saying it right, I'm writing it right and saying it wrong. Okay, so we have here 600 kPa. And then we have 10 kiloliter over 423 is equal to, we have P2, and this guy is 18 kiloliter over 283. All right, so we're going to cross multiply again. So I'm just going to put what the answer is since I showed you the cross multiplying before. It's going to be 600 times 10 times 283 divided by 18 times 423. So you should get an answer here of 223.01 kPa. And the sig figs should be 1, because 600 is the lowest, it's 1. So it's going to go to 200 kPa, right? It's closer to 200 than to 300. Okay, so that's the last part here. So actually, this is the end of chapter 11. So we've learned all about pressure and atmospheric pressure more specifically. We've looked at the molecular theory for gases. We've looked at all three main laws, which are Charles's law, Gay-Lussac's law, and Boyle's law. And this last one is the combined gas law.